Hello, everybody, and thank you so much for joining me tonight. Today, we're going to be talking about Chapter 6, which is Program Performance and Optimization. The main reason why this chapter is included here is because it gives you some of the tools that will allow you to reduce the code and make it more efficient and more beneficial to the ultimate goal of the code. Okay, the things that we are gonna go over are uh, how do we use the structure of the computer basically and the structure of the communication between the CPU, the registers, the memory, the hard drive, and things like that to make sure your code is operating properly. We are thinking here about the assembly code, definitely, but when you type in and write in code, it will uh, go and be translated through a compiler into an assembly code. So the code that you're writing and the instructions you're writing, this is in C or C++, it will affect the execution time, will affect the bottlenecks, it will affect the performance of the CPU and the overall execution time. So it would be necessary whenever we're writing code to think about these things. And you're going to see at the very end, we're going to optimize, but first we're going to make sure that the code is acting properly and it is performing properly. So we are not going to do any programming in this chapter, but we're going to have some tools and we're going to explain them. And when time comes and you're writing code, please come back to this specific PowerPoint to see what can you do to make sure your code is efficient. Today we're talking about efficiency and optimization, but there will be a time where we're going to talk about security. And there'll be other times we'll talk about the effectiveness and the use of resources to write this code. How many people do we need to write a certain program? Because uh, it's not always one person doing the job. Sometimes it will be multiple people, and that's why we have uh, many aspects of project management into writing and programming, writing code, I mean, and programming. So we will go over these aspects and explain a little bit about each one of them, but they will make more sense if you're writing code, and they will make more sense once you encounter the time that some of the code is executing. If the code is simple and not too uh, large, you will not see much of these metrics changing. But if the code is large and you're writing code in the range of several hundred pages long, then the bottlenecks will make more sense, the performance will make more sense. So let's just look at these aspects that we need to keep in mind whenever we're writing code. Okay, the chapter itself is extremely long in the textbook. I do not expect you to go over all of it, nor do I expect you to understand every code that you have in it. It is a high level book, but I made it simpler through these PowerPoints, and I want you to understand these aspects. And of course, if we will ask in the chapters, we'll ask about aspects that we have in this PowerPoint. In the quizzes and the labs, we will go over things simply from what we have in this PowerPoint. Okay, so we make it a little bit more digestible and a little bit more interesting so you can take something out of this chapter. Okay, now these are the main reasons. So we have uh, the the goal from this chapters is basically how to reason about performance, the metrics, the speed up, and the bottlenecks, how to make code faster, maybe optimizing the loops, maybe reducing the calls, maybe referencing the memory less times, and then parallelism, meaning we're using multiple calls in the same time, multiple operations going on at the same time. Okay, so how modern CPUs and memory shape real performance outcomes, we'll see that in one of the slides here. The roadmap what should we be able to do? So reason about performance using clear metrics, as we mentioned. One of them is time, the throughput or the throughput. This is a mistake. I meant throughput. And then the speed up. We'll leave it at that. It keeps trying to change it. And the evidence-based comparison, let's just turn this thing off so we don't keep fixing stuff. Recognize what compilers can optimize and what they cannot. Because some things cannot be optimized, because if you optimize it, it may cause some other problems somewhere else. So you write optimization-friendly code, meaning whenever you're writing your code, you have to think about optimization. So first, think about correctness, of course, definitely. But again, you have in mind a little bit of optimization. For example, if you're writing code and you have too many loops in it, where you could create only one loop, or when you have loops that are calling functions and then each loop will, even if you're repeating the loop, each loop has to be limited, and the calls it makes need to be limited, because every time you're calling on the loop, you may be adding more time in the execution overall. Apply core optimization patterns, improve the loops, as I said, reduce call overhead, meaning not calling too many times on some functions that you don't have to, reduce memory traffic. So every time you go to the memory, you are increasing the time, because remember, the memory is further away from the CPU, so it would be better to just use more registers than the memory. And think about it, as I explained in one of my videos in the past, about the analogy with a doctor and then treating patients. So the doctor is the CPU, the patients are the information or the instructions, or probably the instructions plus the data. And if the traffic between the wait room and the doctor increases, it bottlenecks everything. So it's better to just bring those patients that every doctor is using, put them closer to his treatment room, meaning put them in a register, and then do that. As the doctor needs to get the next patient, he's just going to get out of the room, get the next patient right there by his treatment room, and then so on. And whenever he needs a new patient, he's going to call on, that's when we function, call on one of the other patients, and the nurses will go get him the next few patients, and so on. So there is some aspects exactly like this that happen in the CPU treatment of information and treatment of the instructions and the data. And it makes great sense if you think about this analogy of the doctor and patients. Explain why modern CPUs and memory systems shape performance outcomes, stalls, caches, dependencies. Develop a practical workflow, identify bottlenecks first, then optimize and remeasure. As you see here, see how we are basically create a code, and we optimize it for performance, of course, first. And then we start looking into what is causing all these problems, what is causing the bottleneck, what's increasing the time of the execution of this specific code. And then once you find those bottlenecks, then you need to reduce the bottlenecks, and then optimize, and then remeasure again, see how the speed is improving, and so on. Now, capabilities and limitations of optimizing compilers. So some capabilities and limitations. So there is things that you can do, some capabilities for optimizing, and then there's some limitations you need to consider. Now, compilers can remove redundant work, especially if they are smart compilers, and we have those nowadays. They can reorder instructions, they can use registers efficiently, meaning instead of sending the info to the memory, they just share it, they just put it right there at the registers for the CPU to get next, but only when it is safe. So sometimes you do not want to cause a bottleneck for the CPU by using the extensively the registers, because you need to leave a little bit of space. You call on things, and then you move the data that you're not using in the registers back to the memory. So what do you move and what do you bring in? That is the question. Of course, you may think here, well, I don't know what kind of programming I'll be using to do this kind of stuff. But when you're doing C programming or C++, you are talking directly to the hardware. That's the difference between C++ and C, and then Python, for example, or other programming languages. Because C and C++, they are made to talk to the hardware, and you have a say into that. How does the code talk to the hardware? How does the code affect the CPU executions and performance? So next bullet is many optimization depend on what the compiler can prove by aliasing, side effects, and control flow. These are all definitions you may encounter whenever you're doing code, and each one of them means something. So the aliasing, you're renaming or you are labeling data somehow so you can get it whenever you need it. Side effects, if there is any problems whenever you're creating or optimizing the code. And then control flow, that's definitely when you're dealing with the memory and the registers. Small code changes, type, pointers, function boundaries. As you see here, types meaning what type of data are you using for this specific instruction? Is it text, numbers, char, whatever it is, or characters, I mean. Pointers, where are the pointers pointing at? So when we say pointers, that's basically what is the next instruction we're going to treat? What is the next data we're going to get? So the management of these pointers and what is the next instruction is important. That's where if you have a loop, that's basically what it's doing. It's pointing on something, it's executing it and going back to the code and then keep going. So if you're calling on pointers and if you are calling on some instructions too many times, and really there is a way to not do that, then that's what you do. So make sure you take advantage of this specific idea of small code changes. Use small code, meaning you move and change things little by little. This can block or enable optimization. So small code can help, sometimes it cannot. So remember that. Key mindset, the compiler is powerful, but is not mind reader. So write code, the compiler can optimize. You would not see this unless if you're doing a lot of programming, but it is important to know that this is something that you have to think about whenever you're writing your code. Think that if you are writing some code, of course, first you do it for correctness, meaning you're doing it for a code that is executing properly. You're not thinking about the time or the speed at first, but then you have to think about optimization when you're writing the code. Maybe if you're thinking, I'm reusing the same loop, I'm using it at this place and then maybe 3 pages down, I'm going to use the same, I'm going to call on the same function that has a loop, it has some called functions within the loop. If you're doing that, you may think about not repeating the same thing, maybe creating that specific loop in a way that where you have more functions included, so you call on functions instead of calling on a loop or starting the entire loop. Because you can get the result of the same loop from somewhere else and calling on the result itself without calling on the entire loop to run again. Now, expressing program performance. Performance can be expressed using execution time, throughput, and speed up. So throughput, how much data is being outputted. Execution time, self-explanatory, and speed up is basically a speed up of the CPU executions of the instructions, and at the same time, the data flow and exchange between the CPU, the register, and the memory. Speed up is always relative. So speed up is what? That's basically the time of the old execution divided by the time of the new execution. So we did talk about this in one of the other chapters, which means if we're speeding up something, does it really matter if we're not gaining much time? So when you're trying to speed up something, you have to think about the parts of that code. What can you speed up in this code? And if you speed it up, does it really move the needle for the whole code or not? Because if it's not, there is no need to speed it up. Because if you're speeding up something, there's always limitations somewhere else. It may cause other bottlenecks somewhere else. So use consistent measurement practices, same input size, same machine, same build settings. So you will not be doing a good measurement if you're changing the inputs. Okay, so if by changing the input size and you're thinking that's is changing the measurement, that should not be the case. You should not be doing that. You should allow the execution to be almost the same with the same inputs. May change the code, but you need to make sure the output is still the same. And this way, you know it's the correctness first and then the optimization. Okay, so that's very important to maintain the code operating the proper way. As I said, this chapter here talks about high level, and you just have to keep this in mind. And these ideas will come up later on if you're doing some programming. We're not going to do much of the programming or C or C++ specifically, but I want you to understand that whenever you're doing this type of programming, these uh, performance enhancement methods, they really matter. Interpret results carefully, faster, must be demonstrated with evidence, not assumptions. Program example. So optimization is best learned through a concrete baseline program or systematic improvement. So this concrete baseline, that's when you run the program and it is executing properly. Only then you can start changing things, and you're going to use the same inputs, consider the same outputs, meaning that you want to have the program executing properly. And then you want to see what kind of systematic improvement you want to add to it. Start with correct code, as I said, then profile or measure to find where time actually spent. You can do that by seeing, for example, how many instructions are you executing? How much data are you utilizing? And then when you're executing, what is the workflow exchange of the data between? Is it between the CPU and the register, or is it between the CPU and the memory? All that, or between the register and the memory. You can calculate all that. Of course, it will take a long time to add up these times, especially if you have a lot of instructions, a lot of data to be moved between CPU, register, and memory. And you add them up and you will see, okay, so this instruction, let's say it's instruction of a couple pages, which has, let's say, 300 instructions in it, and this much data being moved. You calculate all that and you can tell, okay, so if I leave the code like this is how much time it will take to execute the entire code, okay? And then you change the code somehow, try to remove or make it easier, especially if you're optimizing the loops or if you're optimizing the branches, if you have branches and things like that. Once you optimize them and you make sure that the program is still executing properly, then you measure it again after you optimize the entire code, and measure it again and see, did I reduce any time in the code execution time? Okay, so if you do that, you'll understand, or you'll find out, okay, so we did decrease the time of execution for this code, and that's exactly what we want. Treat optimization as an experiment. So change one thing, measure again, and compare. That's the logic, okay? Build intuition for which change matter and why. So that's something that comes with practice, practice, practice. You'll be able to see what are the things that we can really play with. As you are typing the code, you'll know, oh, I got to this loop, or I got to this branch, I probably will replace it. Maybe I'll create a function that will call on this. This way, I can reduce the exchange of the data between the CPU or maybe the registers and the memory, and it will increase the performance of the entire code. Eliminating loop inefficiencies, important, right? I keep talking about loops because that's what a lot of code has generally. Loops often dominate runtime, okay? So often small loop improvement can yield large overall gains because it's repeated many times. So if you have a loop that's using less instructions, that's using less time, that means if you're especially using this loop, let's say 300 times, that's going to reduce the execution time for the entire code dramatically, okay? So common fixes: move loop invariant computations outside the loop. So make the loop simpler, less computation inside the loop. meaning it's almost like you have a loop and you have many executions within the loop that you can take out and you can call on them whenever you need them. So reduce repeated work per iteration. If there is a work that can be done only once, you can call on the results of that work instead of calling on the work itself. I hope you understand what I'm saying here. So if the loop executed and it's the exact same loop, so call on the result of the loop instead of calling on the work of the loop, entire work. Okay. Use appropriate data types and bounds check to avoid unnecessary conversions or extra operations. So if you have a data type that you're going to be using for a certain loop or for a certain program, you need to make sure the data type is used, fixed and updated the very first time you use it, because either that or you're going to end up having to do the conversion every time you use that data type. Okay, so if it is a number and you're going to use some code and you're going to convert it into a character because you need to do some operations and it only needs to be a character or a string or something like that, and you have to do it every time you run the loop, that is not proper because you're adding more work within the loop. So if you specify the data type before you run the loop, this way, this operation of conversion will be only done once and the loops will be using the data that you give it, okay? Always confirm correctness after change. Micro optimization can induce subtle bugs. So as I said, sometimes you fix something from one side and it causes problems somewhere else. So you need to be careful. That's why you measure all the time whenever you're doing the optimization. You measure, are we still executing the code properly? And then are we executing it in a better time than what we did before? So you need to make sure the speed up is still happening, because if you are running a code and it causes some bottleneck somewhere else and the time is taking longer, that means that optimization you just did, you need to be reversed. Reducing procedure calls. So procedure call introduce overhead. That means we call in on another function. Parameter pass in. You're asking for a parameter. That means you're calling on stuff within the call. And the return mechanics. Sometimes you return its data type and then you still need to convert it, or you're returning a data type, but it is still not enough because you have to do something to it to be used by the next iteration or by the next function. So you have to think about these mechanics. And then finally, the potential stack activity. So where is the pointer and how much data is in this stack? If you are calling on a stack that is a large stack that you don't need all the data in it, it basically just increases the time of treatment of the information. Think of it as the doctor we mentioned. Imagine this doctor has to treat several patients. Let's say that day he has to treat, let's say 20 patients, and he just asks the nurse, bring me all those patients, put them right next to me in the registers, and I will treat them as I go. That doctor will automatically cause a bottleneck to himself, right? So it's not going to work properly. That is why whenever you call on the data, you call basically only based on the availability of registers you have. And that's one of the reasons that some of the smart compilers, they actually could take that into consideration. And they rarely overtask the CPU because it's using the registers properly. Inlining, which is manual or compiler driven. Inlining can reduce overhead and expose more optimization opportunities in fixing the code. Balance, fewer calls can improve speed, but excessive inlining can increase code size and harm instruction cache behavior. So when you say instruction cache, that's when you bring an instruction from the registers. When you hear cache, we're talking specifically about the registers. Key idea, optimize hot paths, functions called many times inside loop. So we optimize how many functions we're calling inside the loop. So it's better to have a loop that has less and less functions called in, because it will simply just increase the time of execution. Eliminating unneeded memory references. So when we hear memory references, we're calling on the memory, or we're sending data to the memory. So the same logic again. Think of the memory as the main patient's waiting room at the hospital, right? And think of as we talked about, like the registers are the few chairs that you have right outside the doctor's treatment room. So memory references meaning that we are calling on patients from the waiting room too many times. Do you think it would be logical to call too many patients for this doctor? Or do you think he should be treating some of the patients right by his room? When he's done, then he calls on the nurse and it brings him more patients. So that's the same logic here. If you're calling on patients in and out from the main room and bringing them to you, and then replacing some of the people by your room with other patients, and then so on. So there'll be a lot of exchange between patients from the small room to the main room, which basically means from the registers to the memory. You don't want that. You want to limit the exchange of data between the memory and the registers, and only do that when it's needed. Every time you call on the memory, you are increasing the time dramatically, because if we did one of the exercises we talked about in the previous chapters, is the time between the CPU and the registers, and the time between the registers and the memory is around 300 times more. So if a second, or it's not going to be second, it's microseconds between the CPU and the register, it's 300 microseconds between the CPU and the memory. So, or the register and the memory. Generally, the communication is between the register and the memory. So that means the time is considerable every time you call in on something from the memory. Second, bullet compilers try to keep frequency used values in registers, but aliasing can force consecutive reloads. Aliasing meaning you're labeling data and you're sending it to the memory. That's what it means here. You're labeling the data and you're saving it in the memory. Labeling meaning you're giving it an address. Remember that the registers have multiple registers. Each one does something, as we explained before, right? But the memory is using addresses. Every address is used in a certain way. And when you have a list of addresses, that's when we call it a stack. Let's say we have a pointer and we're going to tell it, okay, we're going to put this data in the memory spaces from memory space 1 until memory space 200, for example. That stack has 200 spaces, okay? So you don't get too confused with this. So memory has addresses, registers have register names, and there is only limited number of registers, and they can only store a certain amount of data while the CPU is treating it. Use local variables and clear data flow to help the compiler prove values don't change expectedly. So local variables and clear data flow. When you hear that, it's definitely just talking about the registers, and we using the data right at the register level. Clear data flow, meaning every time you have to bring something, think about the data that is already sitting in the register. You have to move that to the memory before you can use it. So this is basically the clear data flow. And if you are moving data between the register and the memory, you have some registers that are free that you can be using. So this logic, it makes a huge sense if you want to remove the bottleneck for the CPU, because this is exactly what causes problem for the CPU. If it is waiting for a register to be freed, and this register cannot be freed for several iterations or several instructions, and that should normally matter for whenever you're writing the code. You think, oh, I didn't clear the data flow. I'll have to make sure I clear the data flow, move stuff to the memory before I can start the next execution. So reduce memory traffic first. Arithmetic is usually cheaper than memory latency. So when we say arithmetic, who's doing the job here? That's the CPU. CPU is doing the arithmetic or arithmetic logical unit, so the ALU, is doing the job which is within the CPU and actually generally between the CPU and the registers. So these arithmetic operations, if you can increase the operations that the CPU is doing with the registers, instead of calling on stuff from the memory, then you are optimizing the speed. Because as I said, every time the CPU goes to memory, we have a problem. Not have a problem, but we're increasing the time of execution. So understanding modern processors. These are things that the processors nowadays are doing automatically. So modern CPUs use pipelining and superscalar execution, out of order execution. All these definitions, you'll know them, but you can do some research to understand them. Generally, we talked about pipelining previously. We did not talk about superscalar execution. We didn't talk what out of order execution. That's mainly the compiler and the CPU's capabilities can do that. Okay, so the speculation to improve throughput. So the speculation, we're going to talk about it in a minute when we basically see the data that is being called upon is already treated and identified if it is coming from the same area in the memory or not. So sometimes some programs will basically be optimized to a point where it knows if I'm calling something from a certain stack, I'd rather just bring the stack closer to the CPU, the whole thing, because that data that is closer to the other data I needed. The way you think about it is, if you are at a library, and let's say you're doing some research about, let's say, cybersecurity, right? And you went and you got a book from the shelf about cybersecurity. It would probably make sense to look and see, maybe I need few books from the cybersecurity shelves, because I probably will need it again. Instead of me coming all the way to the shelf again and grab another book, I'm just going to grab 10 books about cybersecurity and take them with me to the table in case I need them. That is the logic that we have here when it comes to bringing the data that is close to each other, right? Because it makes probably more sense. And these kind of techniques, they exist nowadays in CPUs and registers where there is smarter compilers and they do this kind of job. You'll see there is another type 2, and we're going to look at it in a minute. Instruction level parallelism means multiple operations can overlap if dependencies allow it. So that's parallelism, meaning we are using more programs and more calls in the same time, and the CPU is basically organizing the entire thing, and the benefit is that the CPU must be faster, or maybe we have multiple cores and each one of them is doing the same thing. So the instructions are running, but think of it like we have 2 doctors, 2 cores. So the data will be treated faster, and we'll have a better optimization if we have the kind of capability. So more cores mean more, less time in execution. So that's basically an optimization process. That's what we call hardware optimization of software. So it is a way to increase the capabilities of a certain machine by increasing the cores, increasing the memory, increasing the cache capabilities of the CPUs. So branches, data dependencies, and cache misses reduce effective parallelism. So these, you'll see them if you're doing code, that you see that the cache misses, meaning we have some data that didn't get picked up properly from the registers, meaning, and we have acknowledgement and things like that between the devices. This is stuff electronics. We're not going to get into that, but generally it means that the CPU is going to have to call on it again and again and again until it gets the right information, because there is some validation tools out there that verifies if the CPU's data that's provided is exactly what we needed or what the CPU needed, and so on. So these are modern processors, and they do that automatically. Optimization is about feeding the CPU predictable work with good locality and few stalls. Stalls, you know what it means? It means delays, taking too long. Now loop unrolling. So unrolling reduces loop overhead, fewer branches, and index updates per unit of work, meaning we're making the loop more efficient. That's what we call it. This means unrolling. We're looking into the loop with a deeper look and seeing where can we limit and create fewer branches, fewer index updates, meaning we're not calling too much on the memory per unit of work. When we say unit of work, meaning either an instruction, one, or a call to a memory, it's a 1 unit of work. And someday we'll talk about why is this important. Unit of work is something we use to calculate how much this program will, how much time this program will use, as I explained in the beginning, by calculating the time it takes for every single instruction, every single call, either to a function or to a code of some kind or a loop. You will use that to identify how much time this loop is taking, right? This kind of work is important whenever you're running a code or a program and it's taking too long. Then you and a whole bunch of other people working together to making sure this program is running faster, especially if you're doing it in some high-level programming, like in gaming or things like that. You want the speed does matter when you're doing that. Okay, you don't want to be moving or shooting in one of those games and it taking too long. So those things and those people who are creating those programs, they first create them to be executed properly, but at the same time, they optimize it because the speed does matter. Hardware does help, but that's why they are expensive, as you probably already know. The computer and the mouse, the keyboard, all that, whatever tools they're using to play a game, they matter tremendously because of the speed they offer. If the speed of the hardware is high enough, there will be less lags caused by the CPU communication with the registers and the memory. So the trade-off, larger code size may reduce instruction cache effectiveness. So the instruction cache, every time we mention cache, think registers. Use moderate unrolling, enough to reduce overhead without bloating the code, meaning without increasing the code. So increasing the code, you know what it does. It's increasing the time of execution. It's all about time of execution in this chapter. Enhancing parallelism. Parallelism, as we said, that's when you are having multiple functions operating at the same time. Can be at multiple levels. Instruction level, within a core, data or task parallelism across cores. So when we say core, CPU cores here, okay? Rearranging computations can expose independent operations and reduce dependency chains. So when we rearrange computation, that meaning you are rearranging the time or the ALU, the arithmetic logical unit, time of executions. If you're rearranging it, can expose independent operations and reduce dependency chains. So let's say some operation needed to happen first, and then second, another operation, you do a loop and you call in the first operation and so on. Sometimes if the operations depend on each other, that's this dependency chains we're talking about, you do not want to change the order of these computations. You have to keep them in the same time. But if you're using loops and these computations are within loops, then it may cause you some problems. Okay, so it is important to know that when you are rearranging computations, some things may go wrong, and you need to keep that in mind if you have some debugging to do at the end. Associativity and reordering can help, but must preserve numerical logical correctness. Okay, numerical and logical, that's what these computations are all about. Okay, so just it's the same kind of phrase, but talking about the same thing. Keep the CPU busy, but minimize the serialized dependencies. When we hear serialized dependencies, when you have something depending on something else, you need to make sure that orders are maintained. So serialized meaning dependent, and they happen in a serialized fashion. So there is an order of these dependencies. So you wouldn't see it until you're actually doing some programming, and you're seeing that some data, if you change it or change in some functions, you start in one function before another, then you will see some changes in the outputs. And then, of course, that's not what you want, because all of a sudden your code is not operating properly, and you have to just think twice about whatever optimization you just did. Summary of results for optimization combining code. So a systematic approach shows cumulative gains. Systematic approach, remove inefficiencies, reduce overhead, reduce memory traffic, and expose parallelism. So you see these, that's exactly what we talked about the entire time here, right? The inefficiencies, reduce overhead, reduce memory traffic, and expose parallelism. The same exact aspects are always what's causing the problems for our codes. So just remember these four. You know, if you see it in an exercise somewhere, that's what it is. That's a systematic approach. That's what we want. Improvements are not additive in a simple way. Bottlenecks shift a code speed up as code speed up. So when we say shift, meaning you may fix one thing from one side, you made it faster, but it caused another bottleneck somewhere else. So you may think twice about what optimization you're doing. That's why the measurement is important. Every time you do something, increase something, you have to measure again the entire code and see if it is still operating the same way. There is tools that do that, by the way, that can, as you're doing your code, it tells you how much time it's taking. You don't need to really add up all the stuff. That stuff is done by some tools that you can, but some big organizations, they spend the money for those type of tools. Measure after each step to confirm actual gains. The most reliable optimization improve the common case and reduce stalls. Most reliable optimization. So again, we need to add here and maintain code efficiency, because if you lose the code efficiency, your optimization is useless. Some limiting factors. Amdahl's law, we talked about it. We even had a discussion about it, meaning that some parts may be able to change or optimize, but the gain may not be worth it. The effort may be too considerable, but you're not gaining much from those parts. So you have to look for the parts in a code that will move the needle the most, and that's what you need to focus on. So overall speed up is limited by a portion of execution that cannot be improved. So if you're improving a code in certain parts, but the rest of the code cannot be, you're not gaining much. Data dependencies, branch behavior, memory latency place hard limits on achievable speed. So watch here what the hardware does. So this is the data dependencies. So if you have better hardware, multiple cores, multiple caches, meaning you have more registers to play with, the data dependencies and the branch behavior, all that will be reduced. So you're gaining more by increasing the hardware efficiencies. We don't talk about that much in this chapter, but I try to keep it in mind, because that's what, throw money at it. That's one of some of the organizations, that's what they do. They want to increase the speed, and you see it probably in your own organization. From time to time, you see them going from one computer to another. At my work, we started from, i3s. Our computers, at first, they were i3s. Not long ago, now all our computers are i7s, because the organizations saw there is a value in increasing the performance of our computers, because when you scale it, you are gaining tremendous time. Because if you have a old computer that's not performing fast enough, And that's when you are doing like data analysis or something like that, and it's taking you a couple hours to do stuff that the new computers can do in 2 minutes, then you gain in a lot of time. So you gain in like an hour and 58 minutes every time you perform that specific task. Optimization can hit diminishing returns, large effort for small gain. So you'll have to think about it, of course. Am I going to spend this much effort and I know I'm not gaining too much? So sometimes you just have to decide what you're going to sacrifice, or are you just going to keep the same time? Prioritize changing that target the dominant costs, hotspots first. Makes sense, right? Hanging fruits, like they say. First, take care of the hanging fruits. So understanding memory performance, memory hierarchy matters. So the registers, as we said, as the cache, then to memory, then to storage. And as you go further away from the CPU, CPU is closer to the registers. As you go further, you're increasing the time. So increasing latency, increasing capacity as you go this way. If your operations start going the other way, from storage to RAM to cache to registers, and that's what we gain when you have multiple cores, because you're going to have more caches and more registers. That means all the operations will be happening right here instead of getting to the RAM and the storage. If you do that, then you're gaining much speed. So locality is the key principle. So temporal locality, reuse soon. Spatial locality, nearby access. That's what I mentioned about the example of the books. When I said, if you're getting some books from a shelf, better to get many books from the same area because you may need them. That's called nearby access. Temporal, reuse soon. So, for example, same logic can apply for the library logic. You have a book, and every time you use it, and if you're not using it, you take it back to the shelf. Imagine how many times you have to go back to the shelf every time you want to use that book. What is the most logical thing to do? Is it to keep that book on your table and use it every time you need it, even if you just used it? Normally, the logic says, I just used the book, I got some resources out of it, I got what I need from it. Normally, I don't have no logic to keep that book on my table, right? That's it, I'm done with it. But I don't know if I'm going to use it again or not. So normally, I should take it back to the shelf. But with this logic here that you see, it's called temporal locality, reuse soon, we have the assumption that maybe I'm going to need this book again. Maybe I may think, maybe I may find something that I may take out of this book. So I'm going to keep it on my table. When I say keep it on my table, meaning I'm going to keep it in the register. I'm going to keep it closer to the CPU. Maybe I will need to use this information again. But there's no need for me to take it back to the memory, and then whenever I need it, to go get it from the memory. Same logic, book at the shelf. Okay, keep it on the table best. So these, how you understand these two concepts is by thinking about library and books. Cache misses can dominate runtime, making fast CPU code irrelevant if data access is slow. So cache misses dominate runtime. At the beginning, remember we mentioned something else that dominates runtime, which is loops, right? But now they're talking cache misses, meaning you brought some data to the register or to the cache, the area closer to the CPU, but you didn't bring it properly, or it got corrupted somehow. If you got corrupted, you have a bigger problem because you cannot trust anything that you're bringing now to the CPU. But it does happen. There is data collisions, there is bottlenecks, there is power fluctuations. It may mess with some of the components of the computer or the hardware, and you may end up with some cache misses. This happens all the time. That's why you have this acknowledged, unacknowledged aspect that you have between these devices that's detecting if the data that came is proper, if the data that came is actually exactly what I needed. So these are things that are out there. Redundancies are created that will make sure that the data, the cache misses don't happen. So this fast CPU code, it doesn't mean anything if the data you're getting from the cache is wrong. So if the data access is slow, because guess what? Why is it slow and you have cache misses and now it's slow? Common sense, right? Because if it cache misses, meaning the data that is brought from the memory to the registers is not proper, guess what's going to happen? The CPU will call in on the same data to bring it again from the memory. It needs to verify if the data is what it's receiving, and that call to the memory increases the time, making the data access slower. So good performance often means organizing data and access patterns for cache friendliness. So organizing data and access patterns. So the data, how it is organized, type, and all that, and the access patterns. Where are we getting it from? Registers or memory, and cache friendliness, meaning that it's reliable for the CPU to use. The cache data is reliable. That's what they mean by cache friendliness. Now, life in the real world performance improvement techniques. So use a disciplined workflow, measure, analyze, change, measure again. Common sense. Remember that, because that may be questioned somewhere. Apply high impact techniques first. Algorithm data structure choice often beats micro optimization. So micro optimization, you know what it means. You know, you're not optimizing too much. You're just optimizing parts of the parts of a part. You're not gaining too much. But it's better to just organize the data structure choice. Okay. When you do that, you're limiting the mismatches. You're limiting the misused cache or missed cache. All that will decrease the time it takes, because this will be more efficient than these micro optimizations. Use compiler flag appropriately, but validate results for correctness. Compiler flags, that's smart compilers. They have ways of detecting the validity of the data and if you are optimizing properly. Document changes and keep benchmarks so improvements are reproducible. So when they say keep benchmarks, meaning you just did a measurement. If you didn't type it somewhere, you didn't save it somewhere, you're not going to know if you're doing better or not. So every time you increase your code, and sometimes you may have multiple versions, and you have to name every version, and you need to log the speed and the time of execution of every version. So identifying and eliminating performance bottlenecks. Identifying first, right? Because if you can't find them, you're not going to be able to do anything. So bottlenecks are the part of the program that dominate execution time. Find them before optimizing. How do you find them? Generally, because you have to go and look for what is the one instruction or what set of instructions that is taking the longest. That is the time where you need to back up and then see, why is this bottleneck taking too long? So you'll have to fix that before you start working on it, because you may be able to just remove the bottleneck without doing any optimization, because if maybe you have a code that is written wrong or something like that. So use profiling measurement tools and targeted tests to locate hot pads. So there is tools out there that you can use to locate these inefficiencies. Once identified, apply the right fix, reduce work, improve locality, reduce stalls, and increase parallelism. This is what we do generally when we are optimizing. We reduce work, we improve locality, reduce stalls. You know what I mean by improve locality. That's the data where you're getting it. So increase parallelism, meaning we are using more functions at the same time. Final step, verify speed up with consistent measurement and confirm no regression, meaning you're not going backward. So wrap up, a practical optimization mindset. This is basically the ideas that we went over today. I know it is not always make sense. That's one of the reasons why I use those analogies, the library, the doctors, all that, because they help you understand and they help you remember those aspects and those processes. So start with correctness, always. Start with something that works. Then measure and see how much time does it take. Optimization without measurement is guesswork. So remember, measure, but of course they need to add here log that measurement. How much time did it take? Target the biggest cost first, okay? And then improve algorithm hot loops before micro tuning. Expect trade-offs. Fewer instructions may increase code size. Fewer calls may reduce modularity. Remember, bottlenecks move as one part speed up, another become dominant. Goal of this week: explain performance outcomes clearly and propose justified improvement. So the way to remember this specific chapter is just remember how we increase the decrease the performance time of a code, right? Always start from correctness. Make sure what you are running works already. And then look for what is the parts of the code that are taking the longest. See if you can fix that. After that, after you make the changes, you want to measure again how much time did we gain by doing this optimization. If it is enough, cool. But if it's not enough, you may need to go back and look again, see what is the next bottleneck I can reduce, and so on. So you're going to have to do that repetitively many times until your code is performing properly within the time frame that you want. Sometimes you're limited. Sometimes you have to execute something before something else is executing, because code call on another code, and so on. So there is multiple things that that's working at the same time, and there is dependencies in happening. So you need to make sure one part is working properly before you go to the next part of the code. Okay, this concludes this chapter. I hope that you take some time, try to read it again, or try to listen to this video again to understand it a little bit. Try to understand the concept of registers, memory, cache, and the CPU, how they operate with each other. And look at the chapter if you want to go and see exactly what kind of instructions we're talking about. You can do that through the chapter, but I don't expect you to read all of it, nor do I expect you to understand every single code they have introduced there. Okay, just be prepared. The quiz that you have will come straight out of this PowerPoint. So make sure you read it and make sure you go over it before you start your quiz. Okay, thank you so much for your time and patience, everybody. Make sure you reach out to me if you have any questions, and have a good evening. Bye-bye.